Jai Hind all of you. I'm Dr. Rahul Bansal from Ajay Kumar Garg Engineering College, Ghaziabad. So this one is the next video lecture for the electronic devices KC 301. So let us start. So in the previous video lecture, we had discussed about the that how to compute the value of the intrinsic and this N naught and P naught, that is number of electron, or you can say electron concentration and hole concentration at the equilibrium state. Okay, so which was like computed as N naught is equal to Nc multiplied by exponential of Ec minus Ef divided by Kt, and this P naught, that is the hole concentration, was given by the Nv exponential of minus of Ef minus Ev divided by Kt, where this Ec denotes the conduction band energy level and this Ef denotes the Fermi energy level, right? And this K denotes the Boltzmann constant. Similarly, this Ev denotes the valence band energy level, and this K denotes the Boltzmann constant, right? So if I talk about the Fermi level of the intrinsic semiconductor, and if I denote this as like EI, right, Ni, right. So Fermi level of the intrinsic semiconductor, like EI, if I consider this as like EI, then the electron and the hole concentration will be equal for the case of intrinsic semiconductor, and this is like given by Ni is equal to Nc exponential of minus of Ec minus Ei divided by Kt, where this Ef is actually replaced by Ei here, right. Next is I can also put the value of like Pi will be equal to, that is number of holes at the intrinsic energy level, it will be equal to Nv exponential of Ei minus Ev divided by Kt, right. So through this mathematical expression, these two mathematical expression will help us to find out the value of the product, that is Ni into Pi. So this Ni into Pi can be computed as, if I multiply this by this one, then I will get the Ni into Pi. So which is equivalent to Nc exponential of minus of Ec minus Ei divided by Kt multiplied by Nv exponential of minus Ei minus Ev divided by Kt, which is equal to Nc into Nv multiplied by minus of Ec minus Ev divided by Kt. Now Ec minus Ev divided by Kt, Ec minus Ev will be equal to Ef, that is Eg, right. Ec minus Ev will be equal to Eg. So this is in accordance with the Fermi level and forbidden energy gap, right. So Ec minus Ev divide, it will be equal, if I consider this as like, if I consider this energy level be like Ec and this be as like Ev, then the difference between the two energy level will be your forbidden energy gap, Eg, right. So through this way we can like say that Ni into Pi will be equal to Nc into Nv e raised to power minus of Eg divided by Kt, which is equal to Ni square, right. Next is what we can conclude from this. We can conclude that the product of N naught into P naught at the equilibrium state is always a constant for a particular material and the temperature. Okay. Now, if at all doping is varied, right, then also this N naught and P naught will be same, right. We can find the value of N naught into P naught is equal to Ni square, if at all temperature is varied, right. So this is the main equation that we have got from the our discussion. N naught into P naught will be equal to Ni square. So this relation is called as the mass action law, right. So we had discussed up to now, that is Ni is equal to Nc exponential of minus Ec minus Ev Ei divided by Kt, and Pi is equal to Nv exponential of minus Ei minus Ev divided by Kt, right. So also we had also discussed about the N naught is equal to Nc e raised to power minus Ec minus Ef divided by Kt, and P naught is equal to Nv exponential of minus Ef minus Ev divided by Kt, right. So through this way we can compute the value of N naught, that is the electron concentration at the equilibrium state, right. So carrier concentration, if I talk about, it can be written in terms of the intrinsic carrier concentration, okay, and it may be like represented as N naught is equal to Ni exponential of Ef minus Ei divided by Kt, and P naught will be equal to Ni exponential of Ei minus Ef divided by Kt, right. So this N naught is equal to Nc exponential of Ef minus Ec divided by Kt. Now what you have to do is, we have to subtract and add this Ei to this exponential term. What we will get is Nc multiplied by exponential of Ef minus Ec plus Ei minus Ei divided by Kt. I am adding Ei as well as I am subtracting this Ei value such that it is equal to the previous equation, right. So we can take this Ec minus Ei in one bracket, and we can also take Ef minus Ei in one bracket. We can separate these two. If we separate these two, what I will get is Nc exponential of minus of Ec minus Ei divided by Kt. Now if at all base is same, then this exponent will be multiplied. So we have like discussed in the we have already studied in the 12th classes, or you can say in our high school, right. So if at all these are in the exponential term, then we can multiply these two, right. So exponential of minus Ec minus Ei divided by Kt multiply by exponential of Ef minus Ei divided by Kt, right. So which is equal to, see, this one is actually, this term is actually Ni, which you had like written over here also, if you see carefully. So N naught will be equal to Ni exponential of Ef minus Ei divided by Kt. So this is the relation that we have got from this. Now if I talk about the intrinsic Fermi level position, so in the intrinsic Fermi level position, this Ni will be equal to Pi, or you can say Nc exponential of minus Ec minus Efi divided by Kt will be equal to Nv exponential of Efi minus Ev divided by Kt, right. So this Efi, this is the Fermi level of the intrinsic semiconductor, is equal to half of Ec plus Ev plus half of Kt natural log of Nv divided by Nc. So this is the mathematical relation we like solve for Efi in this equation, first equation, right. So Efi is equal to half of Ec plus Ev plus 3 by 4 Kt natural log of m asterisk p divided by m asterisk n, right. What I have done is, I have put the value of Nv and Nc in this equation, and I have got this equation, where this Mn asterisk and the Mp asterisk are called as the effective mass of the electron and the effective mass of the holes respectively, right. So if you see carefully, if at all temperature equal to 0 and the EC plus EV divided by 2 is called as the mid gap energy, right? So EFI minus E mid gap energy, I am denoting this as like E mid gap, it is equal to 3 by 4 kT natural log of MP divided by MN strict, right? So normally if we see this experimentally and theoretically also, MP asterisk is less than MN asterisk, right? So EI is placed slightly above the middle of the band gap, right? Now temperature dependence of the carrier concentration, right? So we had discussed about the Ni is equal to Nc into Nv exponential of minus Eg divided by Kt. One more thing that I want to add is, in this mathematical expression, if you see, if at all temperature equal to 0, in this case Fermi energy level for the intrinsic semiconductor will be Ec plus Ev divided by 2, which is the exactly at the mid gap, right? If we increase the temperature, it will like vary, right? Okay, so Ni is actually the function of temperature, which is equal to twice of 2 pi kT divided by h square की power 3 by 2 Mn asterisk into Mp asterisk raised to the power 3 by 4 into exponential of minus Eg divided by 2 kT. Now this Ni is directly proportional to T raised to the power 3 by 2. This is the overall summary that I can draw from this mathematical expression, right? So we can postulate that with the increase in the temperature, right, Ni will also increase. That is, intrinsic carrier concentration will increase with the increase in the temperature, right? So if I like discuss about the idea of Ni variation, so concentration of the doped semiconductor with the temperature we can analyze this thing, right? Now next is temperature dependence of the carrier concentration, that is doped semiconductor, silicon, etc. So if I talk about temperature is very low, okay, so we will have the negligible intrinsic electron hole pair and donor electron are bound to the donor atom, right? In the intrinsic region at the temperature, if at all temperature is raised, then these electrons are donated to the conduction bond, and at about 100 Kelvin all the donor atom are ionized. So this is like the temperature range at which this is ionized. So this region is called as the ionization region, right? So once the conduction band electron concentration are ionized, so we will have like N naught is equal to donor number of donor atoms, which is equal to 10 to the 15 per centimeter cube, right? So second one is extrinsic zone. So all the semiconductors will behave like an extrinsic semiconductor with the further increase in the temperature, unless the increase of the Ni, that is the intrinsic carrier concentration, become the comparable to the extrinsic semiconductor, right? Next is intrinsic zone. At the higher temperature, if at all temperature is further increased, right, then above the Curie temperature, extrinsic semiconductor will become the intrinsic semiconductor again, right? So this Ni will be much greater than this donor atom, and the intrinsic carrier become dominate. So this temperature is called as the Curie temperature. Above the Curie temperature, extrinsic semiconductor will become the intrinsic semiconductor. So this is as shown in this graph also. If at all temperature is increased, then first intrinsic semiconductor is converted into the extrinsic semiconductor. Further, if at all we increase the temperature, extrinsic semiconductor will be like behave like the this intrinsic semiconductor, right? So this is all for this video. Thank you all of you. In the next video lecture, we will discuss about some more important topics. Thank you.